All right, so today we're going to talk about the naive Bayes classifier. And today we'll talk about this naive Bayes classifier, which is based on probabilities. And tomorrow we'll talk about support vector machines, which is a classification with support vector machines, which is a different method. Basically does the same thing in scikit-learn. You will instantiate an instance, you'll fit it by passing the features and the labels, and then you'll predict using whatever you want to predict with, exactly in the same way. In this project, the cone detection project, I'm not specifying which method you should use. You can use either one. You might be interested to try out both of them. I did want at least to present to you these two methods so that you know about them and you know how to use them. It's pretty easy. Scikit-learn makes it really easy. But I wanted at least for you to know about them. I only have 5 projects, so that's really only 5 things I can teach you, but I'd like to expose you to a little bit more. Just like the decision tree stuff, had we not missed the day with the hurricane, we would have done that even though it wasn't really required for the project. So it's something I just want to put out there, especially because at some point you're going to run into using Bayes' theorem or some sort of probability-based algorithms, using Kalman filters and stuff like that, are all probability-based and Gaussian distributions and all this stuff. So it's just a common topic that is important. So I wanted to at least present that. I know many of you may not have had probability in statistics. I've never taken a probability in statistics course. I don't want to go into all of the proofs and the derivation. I'm going to try and explain this from an intuitive perspective. I'm going to pull in some of the notation, like here, that P stands for probability, and then what's inside of there is considered a random variable. Okay, and so when you say P of X, that's the probability of observing X. Now, sometimes X might be a discrete class, like I'm going to talk about whether there's a cat in an image or not, or whether the image has orange in it. It may be a binary choice or a multi-class choice. That X could also be a continuous variable. And you could talk about what is the probability of X being 0.2 or X being 0.1 or some actual value in there. So there's different ways that you can represent what that X is inside of there. Okay? Then this probability of X bar Y, okay? It's still the probability of observing X, but it's the probability of observing X given that something else is true. Okay, so the probability of X bar Y, it's what we call a conditional probability. It's if Y is true, what is the probability of seeing X, which is different than knowing nothing, having no other information. What is the probability of X? Okay, so in this example, I'm going to talk about cats and images, and the cat is A is going to be that an image has a cat in it. Okay, that's what A means. And B is that an image has orange in it. Okay, so it's very simplified, how much orange, where's the orange, whatever. This is just a simple example. But if an image has orange in it or whether it doesn't. Okay, so then the probability of A is essentially the percentage of cat images in whatever set you're talking about. It could be a training set, it could be the world or whatever, but the percentage of images that have cats in them, that's the probability of A. So 60%, 80%, whatever, 10%. Okay, and then probability of B is what fraction or what percentage of the images that we're looking at have orange in them. Okay, then we can talk about 2 conditional probabilities. We can talk about the conditional probability of orange given that cat is true. That's what PB bar A is. Okay, so basically that means how many cat images have orange, or how many cats are orange essentially. Okay, then the other one, PA bar B, that's how many cats are there in orange images? And those are slightly different things. Now, in this case, it's really symmetric and there's no difference here. Okay? And you can make an argument, once I get through some of this stuff, you can make an argument, well, why don't we just simplify this and go one way? And the main reason is because in the end, what we're going to be talking about is this something or is it not something? And we're going to be basing that on a continuous variable. So like the orange would be a continuous variable in the end of a more practical example. Okay? So I'm trying to give an intuitive argument here for Bayes' theorem, because if I just put up Bayes' theorem, it doesn't make much sense. You can derive it from probabilities and all of the identities and different properties of probabilities, but I don't want to go there. Okay, but let's say somebody comes and says, well, if all cats are orange, then if an image is orange, it must be a cat. Okay, and that's basically saying that those two conditional probabilities are the same. Okay, so this guy here is, okay, if how many cats are orange? Okay, and this is saying how many orange images are cats. And so someone might make this statement, well, if all cats are orange, then if an image is orange, it must be a cat. Okay, now there's a problem with that statement. Okay, well, it depends. I mean, if the only thing there are in your images are cats, then it's true. Okay, but as soon as some images are not cats, that statement's not true anymore. Okay, so you need to qualify that. Okay, I need to say, well, how many cat images are orange? And in this case, we're going to say all of them are orange. Let's say all cats are orange. Okay, and then let's say I see an orange image. Okay, what is the probability that that's a cat? Before we were saying, well, it's definitely a cat. Okay, but that's only if everything are cats. If in this case, what I've written here is if 70% of all images are cats, then finding orange doesn't necessarily mean I have a cat, because there's other things that might be orange. So I need to qualify the first conditional probability with how many cats are there, for me to get a better representation for how many, if I find something orange, what is it likely to be a cat? So if all cats are orange and 70% of images are cats, then if I find an orange image, it's 70% likely to be a cat. Okay? Now, if this number dropped, if not all cats were orange, let's say only 10% of cats were orange, you would put a 0.1 here and you'd multiply it by 0.7, and you would be 7% likely of having a cat if you found an orange image, according to this. Okay? Now, this is a true statement if you replace the equal sign with a proportional sign. Okay? And what most people will argue is they say, well, we have to divide by something to make all of the probabilities sum to 1. Okay? And they're right when they say that. Okay? But that doesn't help you understand what is the thing we should divide by in order to make it 1. Okay? So what you actually so here's a reason for why we might need to normalize it somehow. So let's say that cats are rare. Okay, that means that only 1% of images are cats. Okay, but basically all cats are orange. Okay, 99% of cats are orange. That would imply that I only have if I find an orange image, I only have a 1% chance of it being a cat. Okay, well, that's probably not right. I mean, you can imagine a case. Let's say that nothing else is orange, and the only things that are orange are cats, then surely if you find an orange image, it's got to be most likely a cat. It has to be a high probability of a cat. So you can see at least here's a counterexample of why you have to divide by something to make this work out. Okay? So the thing here is that these three quantities are not independent of each other. The 2 in the numerator, they can be independent. The number of cats is independent to how many cats are orange. Okay? But if you think about how many images are orange. That's the PB. Okay? And these three things, how many images are orange, how many images are cats, and how many cats are orange, those three things are actually intertwined and they can't be independent of each other. And I've made a little argument here of why you can see that's the case. So let's say that, orange, if orange images are rare, that means that this is low, only 2% of images are orange, okay? And most cats are orange, okay? That means that there can't be very many cats. If there's hardly any orange images, but all cats are orange, the only way that can be true if there's not very many cats. Okay? So in that case, these two things have to be small if that's big. And in that case, you can see here the numbers turn out that if you find orange, yeah, that's 50% chance that it's a cat, even though there's hardly any cats in the images. Okay? So again, these are sort of intuitive arguments. That equation right there is Bayes' theorem. And we've given some intuitive arguments for why that theorem makes sense. Okay? Now, what's the point of that? Okay? And the point of that is that if we can easily measure these things, we can get this thing that might be harder to measure. Okay? So what might we need to measure over here? We need to know, of all of the images, how many things are cats. If we got a training set, we can get that pretty easily. Okay? And of all these training images, how many of them have orange in them? We can get that pretty easily. Okay? Then the other one's a little trickier. Of all of the cat images, how many are orange? So basically then we need to collect together, let's get all of the cat images and forget the rest, and look at what percentage of those things have orange in them. Okay? That's not too hard to get either. Okay? And those three things would help us say, well, if we find an orange image, how many are cats? Okay? Now, the smart ones of you out there are, well, if I can figure out this thing, well, I just do the inverse and do that one. And that's true if you have this simple case. But if orange is not a yes-no thing, if it's a continuous variable, then there's some problems that come, practical problems that come into play. And you'll start to see why some of those might be the case. Okay? All right. So that's Bayes' theorem. And we're going to try to use that to build a classifier. So here's two classes pulled from Gaussian distributions. It's like the ones that we did in the k-means clustering. Okay, so here basically we're going to do a clustering, but supervised. Okay, now rather than k-means not knowing which point is in which class, we're going to tell this classifier which point is in which class. It's now a supervised learning task rather than unsupervised with clustering. Okay, so what I'm proposing as our classifier is we look at these two things. We've got two classes, and we look at, given some particular x and y value, so I pick some particular point in the xy plane, and given that point, what is the probability that it's class 0? And given that point, what is the probability that that is class 1? That's what these two things represent. Okay? And if the probability of class 0 is greater than the probability of class 1, then we should choose class 0. We should predict class 0. Okay? So it's a very simple argument for how, if the probability of having that at that point in my input space is higher for class 0 than class 1, I should pick class 0. Very simple. So, the idea, the concept is really easy here, okay? But how do we get that probability? Okay, that's the tricky part, and that's what we're going to use Bayes' theorem for. Okay? And you could extend this out. You could make this a three-dimensional problem where you have x, y, and z as an input. You could have any number of features. This is a 2-feature example, but you could have something with 10 features, 100 features. I mean, you've already looked. The histogram of oriented gradients gives 33,780 features. So you have to expand this and think in your head, what does this look like in this 3,780 dimension space? Okay, so we can visualize things in smaller spaces, and we'll do examples there, but then we have to think about doing this in a larger space. Okay, so the first thing we're going to need to do in any problem, we can't look at continuous variables x and y. We're going to have to discretize it somehow. I have to break it up into little pieces, because I can't, it's not possible for me to come up with a probability with discrete stuff, unless we're going to do some sort of fancy analog stuff. If we're going to break this into little pieces, we're going to have to look at regions. Okay, so if I break this into a grid, I can say, that particular grid, anywhere in that particular grid, what is the probability of me being class 1 or me being class 0? Okay, and the probability, those probabilities are going to be based on the training data that falls within that grid space. Okay, but in this case, there is no information in that grid space. Okay, there's no data in that grid space, so we're not going to be able to make a prediction in that grid space, with what we've got here. Okay, so what we're going to do is we're going to have to come up with some other strategy other than looking at grids. And what we're going to do, because we can't make that prediction there, is instead we're going to make an assumption. And this is where the naive Bayes classifier comes in. Okay, the naive part. And what we're going to assume is that x and y, these features, are not correlated, that they are independent of each other. Okay? In this example, they are in fact independent with each other, and this assumption is completely valid. Okay? But if, for example, you were looking at trying to classify coins, and you had a feature as the weight of the coin and the diameter of the coin, okay, those things are not independent of each other. Okay, I mean, it depends on the density. I mean, you can't just go direct. You can go directly from diameter to volume, but the weight is going to depend on the density. But there's definitely going to be a correlation there. Okay, knowing the diameter gives you some information about the weight. You still need the density as well. Okay, so those two features are not independent of each other, and this assumption would not be valid. But what we found is, interestingly enough, using this naive Bayes classifier, even for features that are correlated, actually you still get pretty good performance. Okay, so it turns out to not be so bad. Okay, and what you can do with this independence assumption is, if you use the properties of probability, and you just sort of have to trust me on this one, but basically if you assume that x and y are independent, then we can look at the probability given the x value by itself and having class 0. And we can look at the probability of knowing y by itself predicting C0 and get those probabilities independent of each other and then multiply them together. It's like saying, what is my probability of getting snake eyes when I roll 2 dice? Well, the probability of rolling the first dice is 1/6. The probability of the second dice getting a 1 is 1/6. The two rolls don't depend on each other, so I need to take 1/6 divided by 1/6 times 1/6, and that gives me the probability of getting snake eyes. So that independence allows me to multiply them together individually rather than looking at what is the probability of getting snake eyes given I roll two things. I can break it up into individual pieces. So what that means then is that I can look at all of the x values. Basically, I've taken the projection. I've looked up this way. I've looked this way at all the data and pulled out basically all the x values for each one of the points. And I pull out all the y values for each one of the points. And rather than discretizing a grid in the xy space, I need to discretize all of my x's and I need to discretize all of my y's, and just this information alone will give me, given a particular x, for this grid of x, I'm 100% likely to get class 0 and 0% likely to get class 1. Okay? Here I'm the opposite. I'm 100% likely of getting class 1 and 0% likely of getting class 0. And then here in the middle, there's going to be some trade-off depending on how many of each class fall in that bin. Okay? And then I do the same thing for y. All right? So the naive part of the naive Bayes classifier allows me to separate the dependence on on whatever my variables are, in this case the two of them. I can look at x separately, I can look at y separately, and then I can combine them together to get the probability here that I really, really want. Okay? Now, as an example, this data is not independent. Okay, so it's a little weird. I mean, it's still the same shape. It's still a Gaussian with standard deviations in different directions. But the thing is that once it starts to tilt, if I have a high value of x, I'm likely to have a high value of y too. Okay, and so this is correlated. The naive principle down there is not valid. But still, we can use the naive Bayes classifier and to still generally give us pretty good results, even for things that are correlated strongly like those are. Okay? So this is the data set we're going to work with, just to be simple and show you how all this stuff works out. All right, so how do we approximate the probabilities from the data? Okay, we've got all these these magenta and cyan points. We know how many magenta points we have. We know how many cyan points we have. We just count them, and we can get the probability of class 1 occurring is just, a simple equation. What is the fraction of ones that are magenta? And what are the fraction of the ones that are cyan? So we can make, with this, we can make a very simple classifier that says, well, if the probability of C0 is higher than the probability of C1, we'll always guess C0, and we'll be right a certain percentage of the time, and it's a very easy classifier, but it won't be very good. Okay, we want to do better than that. All right? So let's go ahead and we'll take the x data, and I'll show how we would do this with the x data, and then you can just redo it with the y data. But again, we basically need to discretize this into a certain number of bins. And here I think I have 2, 4, 6, 8, 10, 12, 14, 15 bins. So basically, you need to make a histogram of all of your x data, okay? And that will tell you the probability of x, the probability of this range of x. The probability of this range of x, probability of this range of x, etc. Okay? Just like if you have taken probability, if you have some sort of probability distribution curve, and you say, what is the probability of x being exactly 1.6? The probability of that is 0, actually. You have to look at a range to get a probability that's not infinitesimally small. And that's sort of the same idea here. We need to break this into bins, and we need to say, what is the range? Now, obviously, the smaller the bins we can make this, the better resolution our classifier is going to have, and the better of a decision boundary we'll be able to get. Okay? Because that's what we're after in the end, is we want to draw some curve to separate, the region of the xy plane where we're separating class 0 and class 1. All right, so we've made a histogram with all of the data. Okay, then we can make a histograms here for the class-specific data. Take just class 0 and make a histogram of just it, and just class 1 and make a histogram of it. Okay? Now, one thing we do want to do in order to turn all these things into probabilities, we need to normalize them. Here's this normalize idea coming back over and over again. One of the things about a probability distribution is the sum of them, or the integral over all of them, has to go to 1 or 100%. So we need to normalize these histograms so that the sum of all of the bars equals 1. In each case, the sum of all the magenta ones equal 1, the sum of all the cyan ones equal 1, the sum of all the black ones equal 1. So we need to normalize them, and when we do that, then this thing here tells us the probability distribution for x, p of x. And this is where x is now a continuous variable, or at least in this case a discrete variable that can change. And so now x is not just is it a cat or is it not a cat, it's a value. Okay, so the probability follows this thing of this histogram, and down here this says what is the probability of x getting x given that I'm only looking at class 0. Okay, so if I have class 0, this is the most likely x. Okay, and that x has what, a 22% chance. So if I have if I know my point is class 0, there's a 22% chance that it falls in this range of x values. That's what these probabilities are telling us. Okay, so now we're able to get p of x, we're able to get p of c0, p of c1, and then the conditional probabilities. What is the probability of getting a particular x value given that c0 is true or c1 is true? All right? So what we can do now is we can apply these things to Bayes' theorem. Okay? And so this is applying Bayes' theorem to class 0 and the x direction. And this is applying Bayes' theorem to C0 and the y direction. Okay? So remember, those quantities are telling me for a given x position, what is my probability of having class 0? And for a given x, that's what this thing says here. Right there, that's for a given x position, what is my probability of getting class 0? And this here is for a given x value, what is my probability that I have class 1? Okay? And if we plot that, okay, the magenta ones here are that thing. If I'm at an x of this value, I'm 100% likely to have class 0. Okay? You can see that if I have a small value of x here, I'm sure to have class 0. Okay? Now, as I get higher and higher x's, that probability starts to go down. I don't have 100% anymore of having class 0. Once I start getting in here, if I look vertically from where the arrow is, there's a few values of class 1 there. Most of them are class 0, but there's a few that are class 1. So on the x information alone, I'm still more likely to have class 0 than I am class 1. Eventually, once I get down here, I have a higher probability of class 1. Now I stacked these things together rather than plotting the curve for 0 and then the curve for 1. I stacked them together because they have to sum to 1. There's only 2 classes, so the sum of the 2 probabilities for any given x has to sum to 1. So I stacked them. Okay? So it always sums to 1, and whichever x value here has, whichever color is more dominant at a given x value is which one we would choose, only knowing x. Okay? Now here's curious. Right here, in this region of x, it turned out that I was 50-50. I need to flip a coin. So that must be somewhere right in here, you know, where there's some red ones, there's some magenta ones, and not, you know, basically the same number of cyan ones, essentially. Okay, normalized by the fact that it's more, you're more likely to have magenta anyway. All that stuff is built into this. Okay, so basically, if I was only using x information, okay, at this point, if x was bigger than this point here, I would choose class 1, and if x was less than, I'd choose class 0. Okay, and I can look at a similar thing for y. I mean, y here, I'm looking horizontally at it. At low values of y here are more likely to be class 1. At high values of y, more likely to be class 0. And you can see, you know, we see that relationship there. Okay? Now, our classifier, we want to take into account both the x and the y. We don't want to make a decision only on x or only on y. We want to bring them together. And that what we're going to do is we're going to multiply these things together. I'm going to multiply that times that, and multiply that times that, and compare which one is bigger. And that's going to be my classifier. Okay? So I take those two pieces, the 2 magenta ones, multiply them, the 2 cyan ones, multiply them, and whichever one is higher, that's the class that I'm going to choose. Okay? So I multiply, and you know, I break, you know, that thing is equal to that thing's equal to that's equal to that's equal to that, okay? And these are the ones that we were able to tease out of our data. We get those things out of our data. And as it turns out, this is what the decision boundary ends up being, okay? Now I fudged a little bit. You know, the way, if you, I'll run the code, and the code doesn't look like that. I squished it purposely to make the aspect ratio closer, and I actually flipped it to the way. But anyway, you know, you can see here that in this white region, that's where the right-hand side of this is bigger. And the black region is where the left-hand side is bigger. So I now have a classifier that if I'm anywhere inside the white region, I say class 1. If I'm anywhere inside the black region, it's class 0. So I've now built a classifier to do this. And I've built it, and the code that I'll show you here in a second builds this from scratch, which obviously you're not going to do. You're going to use the Bayes classifier. Okay? Now, we look down at the code, and I mean, I don't want to go through all the bits and pieces, but basically, it does all those things that I've shown, in those slides, okay? And it makes a whole bunch of figures here, okay? There's the original data, okay? There's all the x values, okay? There's all the y values of the data separately, okay? Then this thing here are those histograms for the x's that I showed you, okay? And then the histograms for the y's that are not there, but here they are, okay? And then I have these two guys that are in there, okay? And these will change. I mean, depending on the data is random. I have the data random, so they change slightly. They're based on the same Gaussian distribution, but you can see, they change. That was interesting. If I can get that one to come back here, there didn't fall. No data even fell within that slice, within that vertical slice. There was no data. Okay, and you can see it actually gave an error because it probably did some sort of divide by 0 or something. Okay, so even using 15 bins, I'm not always getting data in there. So obviously, in order to make this sort of thing really good, you need to be, have lots and lots of data, okay, which sometimes is tricky. Then, well, let me get one that's working. There, okay. Then we've got this guy, okay, which, like I said, it's flipped, and it's just because I used an image. I drew it with an image, and it put 0, 0 in the top left corner. I haven't set the aspect ratio, but basically that's your decision boundary. And you can see 2 of the blue points are not correctly classified. Okay, all the magenta ones are correct. Okay, so it's not perfect, but it's pretty darn good. I mean, those two classes are clustered pretty close to each other. Okay, and even still, it does a pretty good job. Now, my guess is if we had enough data and were able to use more histogram bins, more than 15 bins with more data, we would get a decision boundary that is more jagged and can get more things in there, and it would do better. Okay? Now, one thing that's really cool with this, because look at this equation here. Okay? This is a binary decision. Here's a probability on one side, there's a probability on the other side, and we're making a binary decision. Is that thing greater than that thing? Okay? But there's actually more information there. I mean, if one of them is just barely bigger than the other, then that's information that says, well, yeah, it's most likely that class, but actually I'm not that sure. And that information is actually very powerful, to have a classifier that not only classifies, but gives you a confidence in its classification. That's really cool. Okay? So what I did in another figure was this guy. So let's look at that figure and then this one too. Okay? This is the one with the binary decision boundary. Okay? And this one here has the color, the grayscale color is essentially a confidence. If it's purely black, it's like there's no way in hell it's the other class. And if it's purely white, there's no way it's the other class. And you can see you get different shades. So once you pass the 50% gray area, that's what makes this hard boundary. But you can see which ones it's not sure about. It's pretty uncertain. This place here where both the magenta and the blue and the cyan fall in, it's not that sure about that. So there's information there to know, well, be careful in that region when you're making predictions. Okay, so that's pretty cool. All right? Now, of course, in the code, there's all this code. A lot of it's just to make stuff plot right, and I did some copying and pasting stuff rather than making functions for some of these things. So a lot of it is a bit bloated. It's a little smaller than that, okay? But of course, the easy way is to do this, Okay, you make a Gaussian, scikit learns Gaussian naive Bayes. You send it the features and the labels, and then you do a prediction with send something to the prediction, and there you go. You've got the result. Okay, and I've also plotted that one. Okay. So this one. That's the one that I did manually. This is the one that I did, that has the uncertainties. And then this is the one you get from Naive Bayes. And it's a little different, okay? It has one fewer misclassified than what I did, okay? And one of the interesting things that they do in the Naive Bayes, if you read the documentation, is that it actually turns some of the problem into a continuous valued problem. Now, I was talking about being, the grids and the bins and all that, and that being an issue. They've actually solved some of that problem by essentially they take your original data, okay, your original XY data, and they assume that your data is a Gaussian distribution. And it uses the information that you send it to find the center and the standard deviations of that Gaussian distribution. And then it assumes the equation of that Gaussian distribution when it's doing all of its probability calculations. Because it's actually pretty easy to do probability calculations with Gaussians, relatively speaking. You still got to be, quick on the Gaussian stuff, on the probability stuff. Okay, so in this case, I built my data from a Gaussian distribution, so using the Gaussian naive Bayes that they have is completely valid. Okay, much data is normally distributed, but much data is not normally distributed. Okay, so if you have data that it is not even close to a normal distribution, and you use the Gaussian naive Bayes, scikit-learn piece, you might not get very good results. Okay, so you need to be a little bit aware of that. But the problem is, when you're dealing with 3,780 features, how the hell are you going to know whether each one of those things is normally distributed or not? I mean, are you going to go into each one and plot each feature individually and look at what the distribution is? And does it look Gaussian or not? Probably not. You can maybe do a few. Maybe you can come up with some way to automate it, how close it is to get, but, that's a problem. Okay? So that's one thing. The scikit-learn is so great because it takes nothing. All you need to do is do, fit, predict, and you're done. Okay? That's great. But unless you understand some of the background of what's going into these things and how they're built, and honestly, the scikit documentation sometimes doesn't give you very many details. They don't give you the nuts and bolts, so you can't even know exactly what's going on inside of there. Okay? Sometimes they give you little parameters that you can tweak. Sometimes they don't even tell you how they did things. Okay? So, it's very nice and easy to use, but sometimes you might not get the results you want, and you don't know why because you don't know the details of how it's been implemented. Okay? So that's sort of a trade-off. Obviously, you don't want to write all of your code from scratch because some of this stuff gets so complicated. I mean, imagine, I can only imagine trying to write a convolutional neural network from scratch. I mean, wow, it's ridiculous. I can't even imagine doing that. So it's good that these libraries are out there. Okay, so the code that does this is on D2L. Okay, the PowerPoint's on D2L, so you've got those things there. You can look through them if you want. But it's really interesting. There's such a simple thing as this Bayes theorem, essentially, that one probability idea, and you can build a classifier out of that. It's pretty neat. Okay. So we still have a few minutes, so maybe I should talk a little bit about the project that we're going to be doing. Okay, because I haven't talked about that at all yet. Okay, but at least now you have the information about how to make features, and you have the information of how to train with those features. Okay, so you can sort of get started on some of these things. Okay, but this project was inspired by the Vex team, which we got Kyle here. You got your project, and Tim too. Sorry, Tim. I always think Tim and Will, but those are the only ones that I ever work with, so I apologize. And so you guys have this problem where you have to move these cones around. Now, I don't know, do you have to do any of that? Can you do any of it autonomously? Can you do score points if you do some of it autonomously?
Seconds of the match is
Autonomous. Okay. And so, yeah, they have 45 seconds to be able to do some things autonomous. That's not all that long time.
It's not all that long. We have like one of our goals is to be able to run the whole match autonomous.
Really?
Because there's a award you can get for having the best engineered robot.
Okay.
And so we're trying to get that by running the whole match in autonomous mode.
Okay. So one of the things, there's these cones sitting out in this field in different places, and, the robot needs to be able to go and pick them up and put them places and do things with them. Okay?
We have to stack them on those little red cones and the little blue cones in the corner.
Right. So these red and blue ones, they need to stack them on these red and blue ones. You can also stack them on the top of these poles, right?
Yeah.
So that's even harder. So their very ambitious goal is to be able to do all of that autonomously. So that involves being able to know where those cones are and be able to navigate to them. Okay. So I was like, all right, well, this would be a cool project. I'll give you an image. And you need to, first of all, detect where the cones are, okay, in the image, which is useful, okay? And there is a whole line of robotics controls called visual servoing, where all you have is information about the image. You can see where your arm is, and you can see in the image where your thing is, and just using information in the image to be able to get you to pick that up or get near that, okay? This is doing not a pure visual servoing, but rather bringing this back into the real world to know where in the real world are these cones, not just where in the image are they. Okay, and so that's another piece of complexity. So what I've done here is I'm setting that this is going to be the origin. This corner of the field is going to be the origin, and these numbers on there are the numbers, that's the feet in X and Y, where this is the X direction and this is the Y direction. That's the XY position relative to that origin of where those cones are. Okay? And so that's what you are going to do. You're going to not only detect the cones, but you're going to orient them relative to one corner of the field. Okay, so we're going to have to do some image projections and some of these things, more image processing things, actually image formation too, how the optics works in terms of some things. So there's going to be some more machine vision in this. Okay, but this works out pretty well. And the way I made my detection be is that it's going to be the bottom of the bounding box, because the bottom of the bounding box is going to be essentially where the cone is touching the ground. Okay, so the numbers are relative to where the cyan asterisks are, that place on the ground. So for example here, that place on the ground really isn't the bottom of the cone because it didn't get the bounding box very well around the cone. Okay, but in general it's pretty good. Each of the squares in here is a 2-foot square. Okay, so this guy right here, that one right there is 4 feet plus some, so it's 4.2 feet away. That's not bad. And it says it's 1 foot across. That's halfway across that red thing. That's pretty darn good. Okay, so that's pretty great that you guys are going to be able to do this by the end of this project, of not only detect where the cones are, get reasonable bounding boxes on them with this idea of non-maximum suppression to get rid of false negatives, okay, and then use image processing to be able to locate where they are in the image. So that's pretty good information for you. You know where the cones are, relative to a corner of the field. Okay, so that's pretty cool. Now, this kind of does assume a bird's eye view, which you're not going to have for your robot. So you'd have to do some things. You would be able to get distances relative to the robot probably. But it's interesting because there's a senior design project that they're wanting to navigate, autonomously navigate an area, and they're using a bird's eye camera. I'm like, man, you guys you're making it easy for you. You should put the camera on the robot. That'll make it a real project. So, what's that?
9 feet up in the air is how high the camera's going to be.
Yeah, so they have the camera.
Really well with it so far as well.
Yeah, they're working out great.
Yeah.
Cool, but it's still fun. It's still a cool project. So I'm excited to see that one work out. Okay, so that's overall what we're working on. Okay, now one of the things that you're going to have to do in this problem is you need to create your own training data. Okay, so I've given you 2 images. Did I give you 2? Just one? Just one. So I gave you one image, that image, okay, and you need to create the training data. Okay, so you're going to need to pull some pieces out. Where are the cones and get them out. Yes.
I was going to say I went on Google and typed in Vex cones in the image search and downloaded some of
Sure.
the images I found there with that.
Great. Absolutely. 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 That's great. Depending on what is nice about this image is that they're in the environment that they're going to be in. So I don't know those images of the cone if they have the red and the blue and the enclosure around it. If they do, that's even better.
I think 2 or 3, maybe 4 of my images have that.
Yeah. So those are good. That's especially good. But the more images you can get with cones, probably the better. Okay. So what's a little tricky about this one too is that you are going to need to decide on one particular size, unless you want to do this at multi-scale. But I think if you try to do it at multi-scale, it's going to end up running too long. And that is one requirement I set on this project, that when I give you the final test and when I run on the final test image, that it needs to run on my computer in less than a minute. Okay, so if you use lots of different scales, it's probably not going to work. And so you'll notice the cones near the back of the image I have not detected. Okay, because they're smaller, and I've built all of my stuff off of a particular size. I'm looking for a particular size in the image. Okay, and so I'm always looking at one particular size, and then I'm scanning through at one scale. Okay, so that's one thing. If you get images of other sizes, you're going to want to scale them down to be the similar resolution to what this is. Yeah.
This is for training data. Will we be safe to use that method for your testing data?
Well, if you look at the requirements for the project, you get certain number of points for performance in this training image. Okay, so how many does it say? You need to get a certain amount.
I think it's 10.
You need to get 10 correct detections and no false detections in that image. Okay, then this is where you will never see the test image. Okay, I have a secret test image. Okay, and so when I run on the test image, okay, you need to get at least 5 correct cone detections and at most 1 false positive. Yes.
After October 5th, can we get that image? That way we can
Yeah, yeah. So I'll post that image, once it's due, and then you can play around with it, of course. Yep. So now you've gotten into the real world. Okay, real world is you collect a certain amount of data and you train your stuff on that, and you have to do the best you can to make it as general as possible to be able to handle new data that you've never seen before. Okay, and I'll tell you, there are so many researchers in machine learning that don't do that, and they fudge and they cheat on their tests. They report their results on things that they've seen. They don't pull out stuff in the end that has never been seen before. So this is the real best way to do it. Question?
If it was possible, could we go to the lab and take more pictures
Yeah.
than just a single cone?
Sure.
For training?
You can add whatever more information you'd like.
Okay.
You can take lots more images. Go for it.
Okay.
Okay. The way I did it is I only used information from that one image, and I dropped that 5 down to there because that's all I could get. I don't know, maybe I got 6 or 7 or something, but I pulled out my test image after I was happy with mine. I pulled out that test image, saw what my performance was, and obviously I wasn't happy because I didn't get as many, as I had hoped, but well, that's life. And so if that's what I got, I can't expect you guys to do any better than that. So I think I got a little bit more than 5, so I dropped it a little bit for you guys. But yes, please collect as much more data as you want. There's nothing that stops you from doing that. So please, if you'd like to get stuff online, go in the lab and take some more pictures. Have at it.
Okay, thanks.
Okay, so That's it. We'll see you Friday. We'll talk about some support vector machines.
Biggest problem I had with Project 2 was on Saturday night.